morning with this presentation?
Yep.
I did, yep.
Okay, it was 9 megabytes, and I wasn't sure if it was going to go through to everybody. But these days, I think email is a lot more, a lot more accommodating to the size of files. You should see on your screen now something blue that says what you can do in the field. And this is where we're going to start today. It's actually slide 38 of the presentation. Don't be scared. I'm not going to go through all the slides, but what I promised today is that I'm going to give you a list of things that you need to do to get us to be able to give you a quote. And one of the reasons I'm focusing on this is that of 10 inquiries that I get in a given time period for sizing up gearboxes or gear motors, 9 times out of 10, I have to go back for more information. And that definitely slows down the process. I want you to understand that you have a significant technical resource at Weston Automation, let alone the factories that we represent for gearing, Cone Drive and Stober, because we need a minimum amount of information to get you a decent, cogent, and competitive quotation. And that's what I'm going to be going over today initially. And then I'm going to go into a little deeper dive on the technology and the gearing types to give you some background. But I'm constantly going to be referring back to this slide and the one subsequent to it. But this slide is the minimum we need. And if you don't want to call back and you want to get your quote quickly, then you probably want to give us everything on this slide at a minimum. Now, the gearing companies that we represent, Cone Drive and Stober, are engineering focused, and therefore they're not catalog, although they do have catalog products. But for example, the email address ae@conedrive.com, and there's a similar one for Stober. You can literally send in the information that I'm going to be talking about here, and they will quote that to you directly. Or you can come back through us. And typically it's better to come back through us, because if you don't have a complete set of information, then the interface directly with the factory will be more problematic because they're on the East Coast. And so back and forth will be more time consuming. However, if you can hone your talents and your skills of observation to the point where you can get the information that we need, then it doesn't matter where you send your inquiry. I would always copy the Weston Automation person that you deal with. For example, Chris Keller's on the call today. Chris is Arizona. Or you can copy me, because I'm the product guy for gearing, and I can get it to the correct person, whether it's Chris Keller, Chris O'Median in the Inland Empire, Orange County, Chad Christopher in San Diego, Mason up in Northern California, and Todd Price in the LA up to San Luis Obispo area. So with that, first thing, take that flat brain of yours, and what I mean by that is that's not an insult. What I mean by that is that's my slang for your fancy $1,000 phone, and take photos and videos. I need a photo of all nameplates of the motor and the gearbox, or gearboxes in the case that there may be 2 gearboxes. I need a photo of the existing unit in situ, or if you're talking about a new design with an OEM, then item 1, I'll need his nameplate data of the motor he intends to use, and I'll need to see his drawings of the location that he wants to put it in, or some dimensional definition, so that I have the ability to play around with geometries of gearboxes to get the best solution. Again, if it's a retrofit, or if we're at an OEM who's showing us a machine on the floor, a video seeing the machine in operation tells me a tremendous amount of information that I will therefore not need to call you about. So photos and videos, first and most important. Then I need you to define all the speed reductions from motor to driven load. And that means the motor may go through a belt before it connects to the gearbox, or maybe it's mounted directly to the gearbox. So I'll need the nameplate of that gearbox, and then it goes to a belt or a chain drive. That's what I mean by all the speed reductions from the motor down to the load point. And that shaft will be driving the conveyor, will be driving the rotating table, will be driving whatever we're driving. And that shaft, the performance on that shaft is what we're selling. And that's a very important concept. I don't care about the motor and gearbox. I care about that last shaft that we're responsible for and the speed torque curve associated with that shaft. That's what I'm selling to the customer. That's what the customer is buying from us. So a duty cycle is always a difficult subject. And I just want you to describe it. Give me some idea. You won't be able to accurately describe the duty cycle for the most part because the customer won't be able to describe it. There are just a lot of variables associated with this, and getting close or getting some data on this is important. You'll be amazed at what I can do with a 25% description of the duty cycle versus obviously 100% would be great. And then, I don't really need to say this. You guys are all veterans. I need the environment, temp, dirt, water, vibration, anything else that's going to affect the situation. Certain gearboxes are much more sensitive to temperature, and basically has to do with their efficiencies, worm boxes versus other types of boxes. Things you'll learn is that other types of boxes, their mechanical capability, their ability to transmit torque, is somewhat equivalent to their thermal capability. So if the box is rated to transmit 50,000 inch-pounds of torque continuously from a mechanical standpoint, the boxes that are in the high efficiency ranges will typically have an equivalent thermal capability. In other words, the ability to transmit the same amount of torque on a continuous time frame without overheating. Worm boxes are different. And the reason worm boxes are different, especially cone drive worm boxes, is that they have such a phenomenal mechanical capability. You'll see this as I show you the gear geometries because there's so much more metal to metal contact in their gear geometries. So I can transmit 50,000 inch-pounds of torque with a box much smaller than a normal gearbox of another type of geometry, but therefore I'm smaller, less active material, and I'm going to be temperature limited. Double enveloping worm gearboxes, don't let that term scare you, we'll define it in a second, have a 400 to 500% overload capability. Helical gearboxes, spiral bevels, a lot of the other types of gearboxes, no way you're going to get to that kind of level before you break teeth. So we want to understand the temperature environment. So, and going back to the previous item, the duty cycle, because if, for example, my duty cycle is intermittent, I am in the A game of worm gearing because it has a huge ability to accept mechanical loading. And if the duty cycle is intermittent, I don't have to worry about its thermal limitations. So this is the minimum that we need. Now, if you can get more data, great. Those of you that have an engineering background and understand speed torque curves, we are after the speed torque curve of the machine, both continuous and intermittent. That's really important. With the data you give me on the previous slide, I'm going to attempt to define this. And once I've defined the speed torque curve, both continuous and intermittent, I can size the gearbox reliably and efficiently. So there are some other things that we would like to have. And this is the second slide that you're going to want to take with you in order to see if you can get this. Sometimes you can't get it. The stuff on the first slide you should be able to get. The stuff on the second slide, sometimes, especially if you're in an end user situation where you're dealing with a maintenance guy who didn't design the machine, he may not have all of this data. But what you can get will always help us. Speed, torque, curve. In other words, on an XY plot, where Y is the torque and X is the speed, I want to know what that plot is, both from an intermittent or maximum torque standpoint, impact loads, and from a continuous duty standpoint. Now, in certain applications, you may not have a difference between intermittent and continuous. For example, a conveyor that doesn't have that starts very gently. In other words, just runs continuously all day long. That's an application where continuous and intermittent are pretty much coincident, and therefore we only need to define one. That's a very easy application to size up for. But if you've got another application where you're running along at a certain speed and the load is varying greatly from, say, 50% to 150% of the load capability of the system, then we're going to have a lot more work in front of us. And those intermittent duty applications are the ones that challenge us. And we want to be able to get good data, because with the resources we have in terms of gearing, both from Stober and Cone Drive, we have a complete palette of products to solve your problem, and therefore a very unique capability to make you competitive. And we won't be shoving you into a type of gearbox we have, because the optimal gearbox for the application is one we don't have. As you can see, as you go through the gear types in this presentation today, between Cone Drive and Stober, we have all of it. And therefore, I think we're probably your best go-to in terms of gearing in servo or induction motor applications for that very reason. The last two items are commercial ones. Target pricing is the competitor direct or through distribution. Obviously, we will go through distribution for the most part, but if the competitor is indirect, I need to know it, because there's obviously some pricing considerations there. Now, there's a couple of formula that I just want you to be aware of. And these two formulas are the same. Torque equals horsepower times 5252 divided by RPM. This is not metric. This is English standard. If you want torque, in this case, torque is pounds feet, so I probably ought to modify this slide. But torque in pounds feet equals horsepower times a constant times revolutions per minute. That's not radians per minute, it's revolutions per minute. If this were metric, it would be torque in Newton meters equals kilowatts times 5252 divided by revolutions per minute. Obviously, radians per minute is another one that is used in the servo world, but for the most part, we're going to deal with RPM. Now, you solve for horsepower, and then you get the horsepower formula. Same formula. What I want to point out to you is, if we're in the induction motor world, and actually a lot of servos are in the 1500 to 2000 range, know this: an 1800 RPM base speed motor, which is typically a 4-pole motor, and it's the most common NEMA motor in the country by far. It is also a reasonably common servo size. In that case, 52 divided by the RPM is 5252 divided by the RPM is 5252 divided by 1800, which is about 3. And that means that horsepower and torque are related by the number 3. And in that type of motor, a NEMA 5 horsepower, 4-pole, 1800 RPM motor, or 1750 RPM motor if you want to talk about its full load RPM, we're talking about 5 horsepower, 15 foot-pounds. We can immediately make that kind of association. And that's a good rule of thumb to have, because if you are able to define the rated torque of the motor and the rated speed of the motor, that's a lot of data that I can use. Here's rated torque at rated speed. In this case, it's a 3,000 RPM servo motor. Note that if you give me the rated torque at rated speed, below that, I know it's continuous. So I know that I've got torque out of that motor at 1,000 RPM that is equivalent to the torque that you're defined for me. I also know that if you want to go above 3,000 RPM on the motor, that torque is going to diminish, and it's going to diminish linearly. At 6,000, I'll be at half the torque of 3,000. Note that in the intermittent region, limited duty region, another way of saying it, we have much higher torque capability. In this case, it is 0.7 to almost a little bit less than 3 times, so 270% peak torque. And note that the peak torque above the rated speed, also called the base speed, and by the way, a little footnote here, just like lawyers and accountants, engineers use a lot of different terms to confuse people so that you need to come back to them so that they can earn a living. It's sort of a silly thing. I think that the misuse of terms and the use of multiple terms to confuse people is frankly non-productive. However, it is the case. So I will give you the terms that are associated with these as much as I can, as much as I'm aware of them. Rated torque at rated speed. This is also the continuous duty torque and the continuous duty speed. It's also known as the nameplate RPM. Now, above the rated speed, max torque capability falls off. And notice it falls off more dramatically than the continuous duty torque above rated speed. This falls off as the square. This falls off linearly. Now, this line here is a very important line because continuous torque on the left side and diminishing torque on the right side. Constant torque, and this half here to the right of this line is called constant horsepower. If you go back to your formula, you'll figure out that if horsepower is constant and RPM continues to go up, then torque will diminish, right? Okay, very important to understand this concept in terms of electric motors and gear motors. Once again, to the left side, constant torque, to the right side, diminishing torque or constant horsepower. Now, the higher you go above the continuous duty line into the limited duty region, the less number of seconds you're allowed to live there. So along this line here, you're typically talking about 5 seconds or less before the system shuts down. Now, in the old days, we burned something out. But these days, we design stuff for fault trip before component failure. So your amplifier, your VFD, what have you, is going to sense the current associated with this whole situation. That's how it measures torque. Current and torque, we're not talking about electrical in this application, but current and torque are very closely linked between the amplifier, the electric motor, where the current is converted to torque, and the gear train, where mechanical aspect of torque is the thing we're dealing with. So fault trip before component failure. Therefore, the amplifier is going to let you run in this zone here, maybe 120 seconds. You start getting up to this line, it's going to diminish down to less than 5 seconds. And that's how intermittent duty or limited duty works. Okay. Now, we're going to go back up to the top of this presentation to give you a little background on gearing, and then we're going to come back to this application because all the slides between 42 and 61 are the things that we do on our side when you give us the things that are defined in slide 39 and absolutely the minimum in slide 38. So slide 38 and 39, for the most part, well, 38 is your responsibility. Bring that to me. I can't get that. You have to get it. 39, we're going to work together on. And then from 40 on, I'm going to give you a little bit of a picture of our world in terms of what we're doing to size for you, or if you want to get to the point where you can size these things yourself, understanding slides 40 to 61 is really important. So, however, we're going to go all the way back. I don't know a faster way of doing this because I'm stupid with regards to PowerPoint. But here we are, boxes. All right, so desired performance on the target shaft, I talked about it. If you want to make things simple, you're going to make your life easier. And the whole point of this process, this class, is to make things simple. It's not to load you with a bunch of data, because you can get that yourself on Wikipedia. What these classes are about is to show you how to make things simple so you can be efficient and get the stuff we need quickly so we can, quote, be first back to the designer, win the business. Target shaft. We need to define the target shaft, and it's typically the output of the gearbox, which is what we're selling. As I said earlier, I'm not selling a motor, and I'm not selling a brake, and I'm not selling a gearbox. I'm selling performance on a target shaft. And if I can focus the customer on that and away from his motor and gearbox in his mind, and just on that shaft, there's a couple of things that happen. I get the data I need, and I get him off of his brand preferences, because he's always used Allen Bradley servos, or he's always used Nord gearboxes. And nope, just tell me what the shaft is, and I will give you a better solution. At least that's the premise. It's very important. Define the performance on this shaft, and you can accurately specify all the upstream components, and that is a truth, as long as you got the knowledge. And if you don't have the knowledge, then you have us, Chris Keller and myself, and the rest of us at Western Automation, let alone the people at Cone Drive and Stober. Okay, so there again, that speed torque curve, gosh, that keeps coming up. And there, RMS versus peak. RMS is another word for continuous. RMS means root mean squared. Another confusing term. Okay, so here's sort of a repeat of slide 38. But again, you can see same set of data, and I can rock your world. There is, again, that formula. It's a little bit more complicated, so let's not worry about that. Now, here is a principle that I want you to understand, because if you're just running along on a simple horizontal conveyor, that's an easy duty application, as I said before. The minute you start putting inclines in there, you start increasing load. And the interesting thing about it is, as you go off of angle 0, which is horizontal, the worst you can go is 90 degrees, right? That's a vertical lift. So for this instance of application understanding, I can really help you understand the difference between a horizontal and a vertical load and an inclined load with a little bit of trigonometry. The worst case load in this type of is a lifting load where the angle is 90 degrees. Here's horizontal, that's 0. Here's the lifting axis, that's 90. And you're picking up this weight on a drum with a cable, and there's a lever arm here that is the radius of the drum, and that will define the torque. Hoisting is a very easy application to define, because here I have my pounds, feet of torque, and it's always constant. No matter whether I'm at 0 speed on this drum or I'm rotating the drum at 100 RPM, the torque is the same because the load doesn't change. The radius arm doesn't change. Okay, a footnote for you really detailed people. Yeah, okay, the load changes because as you get the load closer to the drum, there's less cable weight, but let's just say that that's not significant. So load doesn't change, radius arm doesn't change, torque doesn't change. This is the classic constant torque application. When people say constant torque, typically it's not constant torque. But in this case, this is constant torque. If you can do a hoist, you can do pretty much anything. Now, once we have defined this, and then we know how fast the lifting speed is, we have our speed torque curve. By definition, this application cannot go beyond the constant torque realm. Hark back to that graph I showed you of constant torque versus constant horsepower. You can't overspeed a hoist, because once you get to the end of the constant torque, as you know, in the constant horsepower range, the torque diminishes. Well, with diminished torque, I can't lift this load anymore. So that's it. It's always in the constant torque range. It's a constant torque application. We can't do overspeeding on a hoist. And once I know the maximum speed of the lift, I know the maximum RPM of the drum, and then through the gear reduction ratios, I can get back to the maximum RPM of the motor. Very easy application to define. What happens when we start to go, when we look at inclines? And here's where the geometry comes in, because the key angle here is theta. It's a Greek letter. And theta is 0 if it's horizontal. Theta is 90 if it's vertical. Okay? And at 45 or 30 or 60, it's an incline. Now, intuition is going to tell you that the amount of torque required, which is proportional to the force, which is what this diagram is about. This force is the weight times the lever arm, which is the torque. So torque force is going to vary from a minimum at 0 or horizontal to a maximum at vertical or 90 degrees. But how do we define it if it's at 45? It's really easy. On an incline, it's proportional to the angle of theta, and fortunately, the sine of that theta angle gives us exactly the number we need to determine the force and therefore the torque. The sine of 90 degrees is 1. The sine of 0 degrees is 0. Now, this is not linear between 0 and 1. It's the sine function. So the force to drag the load up a hill, assuming 0 friction, because we haven't factored in our friction, is the sine of the angle theta times the weight. And in the hoisting application, since the sine of theta is 1, it is the weight, because 1 times the weight equals the weight. But as we go to a lesser angle than 90, we're going to be less than 1. And the function of the sine allows us to get that multiplier, 1 if it's vertical, 0 if it's horizontal, and somewhere between 0 and 1 if we're on an angle incline. Again, a very simple way of handling the sizing issues associated with an inclined plane. If you want more on this, go to this link. It's a pretty cool website. Now, torque and speed. Okay, we've got a pretty good example of how we do torque. Obviously, on certain machines like a packaging machine or a rock crusher or a slitter line, we'll have different ways of calculating the torque. Now we want to look at speed or velocity, RPM, radians per second, revolutions per second, what have you. A typical velocity profile is accelerate, run at a speed, decelerate. Now, this hopefully defines our continuous duty range. The accel and the decel, depending on how fast we have to do these, and depending on how much inertia we have on the system, this is a change zone, okay? This is not continuous. So here, we're going to accelerate, and we're going to require a different torque during this velocity curve section than we're going to require during this velocity curve section. And if the angle of the ramp is the same, again, without friction considerations, torque at acceleration, torque and deceleration will be about the same. In practical matters, torque of acceleration is typically going to be more than torque of deceleration, even if the ramps are the same, because friction will be helping us to slow down. In the decel, it'll be against us during the accel. And you're talking about a 10% factor there. Okay, so here's your typical velocity profile. A lot of applications don't have a flat top. A lot of applications go right, they're basically pyramids. They go accel and decel. What kind of applications are those? Typically point-to-point moves, where you want to get there as fast as possible. So point-to-point moves, as opposed to a conveyor that accelerates to speed, runs for 3 hours, and then decelerates at the end of the shift, two different types of applications. Now, here's a little bit of what reality can do for you, because this is a very nicely defined flat top pyramid, okay? Here is continuous duty, and here's typically what you're going to run into. And why does this line go below the zero line? Well, because it's a reversing application. If this is velocity, and here's your maximum velocity, this is zero. If you're going in reverse, you're going below the zero line. So the red mark isn't just me making a typo and a squiggle. That's typically what you can run into. How are you going to define that? And that's not your job. That's our job. You've got to get us the data. But if you want to do our job, be the applications engineers, great. This is the worst case that you could run into, where your velocity's all over the place. And that's not uncommon. Again, that intermittent versus continuous duty definition. Let's look at a typical application. This is the point-to-point move that I talked about, okay? And I took this off of an application that we're doing where we're using a Beckhoff controller, and unfortunately it was in German, so I put the translations over here. But here's our position. All right, we're moving and we're accelerating slowly, then fast. Here's our maximum acceleration or change in position. The derivative of position is acceleration, and then we start to taper off, and then we come into our final position. This is our velocity loop, our Geschwindigkeit, and we ramp to full speed, and then we ramp to zero speed. This is the acceleration, and notice here's the zero line. So we are accelerating, and then immediately when we change on the velocity curve, we have a step change going to deceleration. The drehmoment or torque of this application is constant. So we have a constant accel of torque, and then to decelerate the load, we have similar torque. Now, this torque is going to point in a different direction during decel than it is during accel, but its absolute value remains the same. And again, this is without the considerations of friction, because obviously friction would retard us in the accel, so we would have more torque here and then slightly less torque during the decel, because friction helps us during decel. Again, about roughly a 10% factor or less. Now, I asked you to define all the gear ratios on that list. Remember that? If we look at the minimum of what we need, just zap this in here. Define all speed reductions from motor to driven load. That's part of the minimum of what we need. Here's how you do it. This is the engine, which is the motor, okay? And your first reduction ratio, your second reduction ratio, and your third reduction ratio. The final drive. Now, you could have one reduction ratio, 2, 3, you might have 7. I need to know all of them. Because if this is the shaft that I'm selling and the performance on that shaft, it's critical for me to understand these gear reduction ratios or these belt reduction ratios. Let's just call them the velocity reduction ratios. And you're going to have to define all of those because I'm not there with you in the field. Why do we use gear reductions? Why don't we just bolt the motor to the load and call it a day? Well, gearing naturally reduces the RPM. So if you're using an 1800 RPM motor and your load shaft only wants to rotate at 100, then you're only going to be using 1/18 of the motor's capability because you're only going to be going from 0 to 100 RPM on a motor that can go up to 1800 RPM constant torque. And beyond that, in reduced torque mode. So if we want to use the motor's full capability, then we're going to use a gearbox with an 18-to-1 reduction ratio and allow the motor to run at its rated torque and rated speed. And yet the shaft runs at 100 RPM. So that's the major reason that we use gearing. And therefore, the cost of the gear has to be less than the difference between the cost of the direct drive motor and the cost of the motor that mounts onto the gearbox, which in most cases it is, because in an 18-to-1 reduction, the motor would have 1/18 the torque when it's on a gearbox than it would be direct drive, because gearing multiplies the torque. Gearing increases the torque. So on a 2-to-1 gearbox, you multiply the torque times 2. Again, we are not talking about efficiency and coefficients of friction yet, which again is about a 10% factor. So you can see that using gearing to reduce the RPM and increase the torque is very important in terms of getting the most economical solution. So therefore, the gearing can reduce the cost of achieving the desired performance on the target shaft. Focused on the target shaft. What are the downsides of using gearing, or considerations, I should say? It adds nonlinearity to torque and velocity control because the gear teeth, as they mesh together, there's a certain amount of force variation there. So if you're into applications like scanning or extremely precise machining, you don't want a lot of torque variability, and that's going to affect the type of gearing that we select for that. We're going to get into types of gearing in a second. Gearing adds backlash. If you're controlling position on the other side and you've got gaps in your gears, the motor position isn't going to be exactly related to the final shaft position, because the gearbox's teeth are slapping back and forth over the backlash between the gear tooth interfaces. So that's a factor. Gearing has efficiency factors. We'll talk about that in a second. Gearing reduces the MTBF of the system because it's a mechanical device, it moves, and it adds parts. And gearing requires maintenance. So this is more just to keep in your pocket as good knowledge because it affects the type of gearing that you select. But the maximum ratios per stage of different types of gearing. This may be a little bit premature for me to show you this. I'll come back to it after I've shown you the different types of gearing. But note that some of these gearboxes have an extremely high reduction ratio capability per stage. So what I want to point out to you is that if I'm using a worm gear and I can go up to 75-to-1, how many planetary stages do I need to get to 75-to-1? 3. 8 times 8, 64. That's not 75. Need another stage. Note here, because planetary is a very common gearing, seems like I see Apex and CMG and Thompson and yes, Micron, all those people, they all make planetary gearing. It's a very generic mass-produced type of gearing for servos, semi-precision, I'll call it. But at 8-to-1 is where I, as an applications engineer, go to a second stage. And I just want to point that out to you because this is one of the most commonly used gearboxes. There are gearbox companies who supply 10-to-1 planetaries in a single stage. I'm going to show you why I don't think that's a good idea. That's just a little point in time here. But the amount of ratio, I mean, look at this. In a harmonic in a single stage, you can get 160-to-1. Okay. Efficiency, another factor in addition to ratios that affects our selection of gearboxes. And the efficiencies are mostly in the 90s. Look at worm. 50 to 90%. What the heck's going on there? I'll explain that. Most of your gearing is going to be helical, inline. That planetary falls along that line. And bevels. Note they're all in the high 90s. Okay. Oh, I'll let you read this on your own time. It's a lot. They tell me not to put a lot of words on a slide, and sometimes that's great, but I'm not selling dresses and shoes here, and this is a technical thing, so I got to put words on a slide. Oh, I should talk about this. Worm gearing, by the way, if I go back to this efficiency range, with the exception of worm, applies across the speed range, and whether you're going forward motoring or regenerative. And I don't mean forward and reverse. I mean if the motor's driving the load versus the load driving the motor. Think of a roller coaster going up the hill. You are powering, you're drawing power out of the motor, driving the gears. You crest the hill, everybody starts screaming, you go down the other side, the load is driving the motor. Now the torque is reversed. It's coming back from the load through the gearbox to the motor. Forward powering and forward powering and regeneration, forward regeneration or reverse powering, reverse generation, doesn't matter. The direction doesn't matter. So when you're powering versus regenerating, positive torque versus negative torque, these efficiencies on most of these gearbox types remain the same. In the worm, absolutely not. Worm gears resist backdriving. This can be an advantage or a disadvantage. It's definitely a disadvantage if you're not aware of it and you size it incorrectly. So note that that is the point I was making on this next slide. So I was about to jump over it and I decided, no, I'm not going to jump over it. So gears have a poor backdriving efficiency. When is that an advantage? When you want the gear to act like a brake or to resist the load driving the position. In many cases, it can be very safe because if your motor's not driving it, you don't want the load to move. If you're using other types of gearing, which have good efficiency, forward driving and regenerative driving, then you are going to be rolling back and forth and you're going to have to apply a brake to hold the load steady. Think incline. As I'm going up on an incline conveyor with a whole bunch of boxes filled with rocks, if the motor fails, the worm gear, depending on its ratio, will either resist sliding back or lock up and prevent sliding back. And typically 50 to 60-to-1 on a worm gear. Remember, we can do up to 75-to-1 in a single stage. That worm gear is going to lock up and that load's not going to slide back. At 30-to-1, 20-to-1, it's going to slide back slowly. Okay. Now, this is too much detail, but for those of you that are into it, it's very important in gear design to understand how teeth mesh together. the contact surface area, the angles, the pressures, all that stuff happens without you needing to worry about it. Here we are in types of gears. A spur gear, the most simple type of gear. Very noisy, by the way, but reasonably efficient if we go back to that efficiency chart. The helical gear, where you have the teeth angled, and therefore the contact isn't so much slapping, which is what creates that noise, but rather it's more of a nuanced contact where you don't just slap together like you're clapping your hands, but rather the teeth come together because of the angled nature of them in a more gradual manner as we transmit the torque between the small and the large gear. Double herringbone, this is a or herringbone double helical. That's same principles of helical, just it's basically two gears. Now, here we get into the right angle stuff. Note that this is always parallel shaft, right? Here we go from this angle to that angle. That's a 90 degree. That's what we call right angle. And we have different types of right angle gearing. This, by the way, is not a right angle gear, but here's your worm gearing, and that's a right angle also. Axis of the driving gear, axis of the driven gear, 90 degrees. Axis of the driving gear, and then there's a bigger gear here, but its axis is the same. It's parallel. So we have spiral bevels, also called helical bevels. This happens to be a miter gear. It's a 1-to-1. It's basically a turn the corner 90 degrees type gearbox. I showed it just to note this is a straight bevel gear. It doesn't have the spirals, the helical effect. So it's the equivalent of a spur gear in a right angle geometry. Here's another spur gear on this rack and pinion. This is another spur gear on this internal pinion versus the external gear. And then we have the worm gear. Again, just some more pictures. This, by the way, here is a cycloidal gear. We're not going to get into harmonic and cycloidal that much today. I don't have the time for it. In fact, I'm really running out of time now. I'll probably hold you an extra 10 minutes if you can stand it. Worm gearing, double versus single enveloping. This is an extremely important thing to understand because worm gearing, if you're using double enveloping worm, becomes a very interesting alternative to spiral and helical bevels. It also becomes an interesting alternative to your inline planetaries if you can turn the corner in the application, because right angle in many cases offers advantages over those planetaries. Now, let's go back to this slide here. The efficiencies. Single enveloping worm is in the lower half of this range. Double enveloping worm is in the higher half of this range. You can see that double enveloping worm breaks the myth that everybody thinks of when they think of worm gears. Oh, they're inefficient. They're cheap gears. No, a double enveloping worm has close to the efficiencies of these. Consider that in a double enveloping worm at 60-to-1, I'm one stage. In a helical gear, I'm going to have two stages, so it's 0.98 times 0.98, which is about 0.95. 0.95 to 90 is even closer. And I gain that advantage because I can do single stage up to 75-to-1. These guys can only do up to 10-to-1. Well, stage efficient gears get closer to the single stage worm efficiency. Okay, now the difference between double enveloping and single enveloping. By the way, double enveloping gearing was a drawing of this concept was found in Da Vinci's files. I actually saw it when I went to the Reagan Library and they had Da Vinci's a display on Da Vinci. Really, really cool display. The guy must have been amazing. But he had a drawing of double enveloping worm. The first commercially double enveloping worm manufactured gearing took place when a guy by the name of Cone, big surprise, started manufacturing this back in the 90s. I'm going to tell you a quick story about how worm gearing A double enveloping worm is now very competitive. This type of gearing on the right is the single enveloping worm. Note, it's a cylinder. It's straight. Double enveloping, we've got a bevel. This is much more complicated to make. And up until about 20 years ago, it was extremely expensive to make because you had to have special tooling, you had to have hobs, and then you machined every one of these geometries from that specific tooling. You wanted a different geometry, different ratio. You had to get them another set of tooling. Obviously, it's very expensive. And you had to hand lap these gears together to get the interface right and to get the efficiencies up. Well, with the advent of 5-axis CNC, the cost of manufacturing double enveloping worms has come very close to the cost of manufacturing single enveloping worms. Interesting, right? Now I get all the benefits of double enveloping versus single enveloping. Well, what are the benefits? Efficiency, I've already mentioned. Tangent is the point where a line intersects the circumference of a circle. And it's by definition, mathematically, one point. Therefore, cylindrical worm gearing has one tooth of contact. If we're not tangent, but we push the axis of the gear of the worm into and closer to the center of the worm gear, the round gear, we're not tangent anymore. We have 2 points mathematically, but if we bevel the surface, we have all kinds of tooth contact between this point and this point. And indeed, double enveloping worm gearing has 4 to 8 teeth of contact, depending on the ratio and the geometries, versus always 1 tooth of contact for standard worm gearing. It's a huge advantage over standard worm gearing. And now that the cost of manufacture is very similar, you get the attendant benefits for a much lower cost. What are the attendant benefits? Well, the higher efficiency, because the tooth pressure is less, because I'm 4 teeth in contact instead of 1. What else does 4 teeth in contact give you? More torque driving capability. So for the same center distance, the center distance is defined as the axis of this shaft to the axis of this shaft, so this dimension right here. For the same center distance, I can put out 30 to 50% more torque with 4 teeth in contact than I can with 1 tooth in contact. My backlash is less, which affects our ability to do precision applications. Significant benefits from the double enveloping worm gearing. Here's the other thing. This is going to have a shock load capability of around 200%. This is a shock load capability of 500%. No surprise, 4 teeth to 8 teeth in contact versus 1. Not rocket science. Okay, so this is the other type of special gearing people are not aware of. It's called a hypoid gear. This is not a spiral bevel. The reason it's not is because in spiral bevels, the pinion would be coincident with the axis of the round gear, the center of the axis of the round gear. Note that this is off-center. Gives us a lot of advantages. Huge ratios for one, and big through bore for another. Now, when you're out in the field and you're trying to tell what type of gearing it is, I'm going to give you a very simple way of telling. And that is because the concept of center distance exists in a worm gear that doesn't exist in the other standard gears. So note that the axis of the input shaft is not coincident with the axis of the output shaft. There are 2 different planes. The axis of the input shaft to the output shaft on a spiral bevel is the same. Let's look at that in terms of reality. Which of these are worm boxes and which of these are spiral bevel boxes? Well, you can tell because here, this input shaft isn't the same, isn't at the center of this output shaft. And if you think about in your head, the worm gearing that's in here, yeah, there's a worm and then there's a round gear here. And this round gear has the worm riding on its outer diameter. Here, another worm gear, because the worm shaft is here riding on the outer diameter of the worm wheel or round gear. So picture in your head the gear set inside this box. These two are worm boxes. So when you report back to me the type of gearing on the application you want me to define for you and help you size, then you can identify worm gearing. Is this a worm gear? Absolutely not, because this shaft runs right into the center of the output shaft. This happens to be a 1-to-1. I can tell that because the two shafts are the same diameter. So it's a miter box. Here, again, same thing. There's the output shaft. Can't even see it, but I can already tell that it's on the same plane as the input shaft. Here again, same plane. This happens to be a giant spiral bevel. These guys are worms. Look, plane of the input shaft, they happen to be all coupled together. This is a multiple. This you're going to see on tube mills and slitter lines and some other types of printers. It's called a drive shaft or a jack shaft, driving all of them. And they're all obviously mechanically linked, therefore they're synchronized. They may not be the same ratio, but they're all synchronized. So here, my input shaft is not coincident with my output shaft, so this is a worm gear. That's how you tell the difference between a worm gear and a spiral bevel or helical bevel box. Again, you see, the axis is on the same plane. The axis is on the same plane. Okay, and if life was always simple, that would be it, but life is not simple. So here's combination. Here is a spiral bevel box with an additional helical reduction that would look like a worm gear because they're not on the same plane. Don't be fooled. Taking a picture is always helpful because with that and the nameplate data, I know which companies make which type of boxes, and I'll be able to help you there. Here is a spiral bevel box. I know it's a spiral bevel because this output shaft is on the same plane as the input shaft. By the way, if you have any questions, just pipe up. But that's a pretty simple concept. Inline gearing. We're not turning the angle here. We're in line. And by the way, depending on the application, sometimes customers spec inline and it's better for him to go right angle or vice versa. And he may have done it for mechanical convenience reasons. He may have done it because he designed the machine that way before. He may have done it because he was initially talking to a guy who only has inline or right angle gearing. Who knows? Again, the point of this class, get me the data, we'll come up with the best solution because we're not biased to one geometry or another. But now we're going to talk about inline gearing. And by the way, inline concentric shaft, where the shafts are in line with each other. And then we'll talk about parallel shaft, where the output shaft is not in line with the input shaft. Planetary gearing is always inline concentric shaft. And that's a planetary gear. Here you have your sun gear and your planet gears driving on an internally toothed final stage. One of the reasons I don't go beyond 8-to-1 in a planetary, I mentioned this earlier, is because these planet gears start to get real small when you get to above 8-to-1, and the box is significantly reduced in terms of its output torque capability because smaller gear, less torque transmission. Therefore, in most cases, I'm going to stay away from anything above 8-to-1 in planetary unless the duty cycle is really light. And I can deal with the reduced torque transmission capability of the smaller diameter planet gears. Okay. A different type, by the way, this gear tooth interface is called involute, where you have basically teeth and internal teeth. External teeth and internal teeth. Another planetary style of gearing, also concentric shaft, but using lobes, not involute teeth, is called cycloidal gearing. Note the amount of surface area of contact here and the fact that there are no precipitous geometry changes versus this, where these gears are slap, 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 right? I've got contact all the way around. Cycloidal gearing has a huge ability to transmit torque, transmit it smoothly, and transmit it with less backlash. So there are cases where we're going to use cycloidal gearing versus traditional planetary gearing. Told you we're not going to talk a lot about cycloidal and harmonic, and we aren't. But this is harmonic gearing also tends to be concentric shaft. This is the subject for another day. These type of gears are very expensive, very precision. They're all zero backlash, and it's good stuff, but not today. Now we have parallel shaft gearing, where the input shaft is not on the same axis as the output shaft. And that's because we were using helical gear sets, pinion driving a bull gear. And here we have two reductions, okay? Here we have, there's a pinion on this shaft driving this gear. This gear drives this pinion, which drives this gear. So inline parallel shaft is another style of gearing. Typically industrial boxes, we're not going to use a lot of inline parallel shaft when it comes to precision. But when you talk about the really big boxes, you're talking about 500 horsepower overland mining conveyors and rock crushers and whatnot. You're talking about big boxes like this. They tend to be called Falk boxes, the same way we use the term Kleenex, because Falk was a big name in the industry, but not so much anymore. But parallel shaft, helical gearing, or double helical, the herringbone, is often used in this geometry to reduce noise. Big bucks here. You know, you're talking about boxes that can cost $50,000. I'm running out of time here, but I want to talk a little bit about how we mount the motor to the gearbox, because that's also important. When you're selling the gearbox, you want to reach out and sell the motor also. Why not? And frankly, reach out and sell the amplifier or the VFD too. But the interface between the motor and the gearbox is really important, especially when the motor is close coupled to the gearbox, as is very often the case, where the gearbox becomes the direct gear reduction on the face of the motor. You can couple a motor to a gearbox where you have two solid shafts with a spider coupling in between, but now you've got a very long axial length, and that's typically not the way it's done. Integral gear motors use a quill shaft design. And that means the gearbox input shaft is a female shaft, and you insert the male shaft from the motor into that. And it's typically keyed, in rare instances splined, because that's more expensive. But basically you insert those shafts into each other and bolt the motor to the gearbox input flange, and now you have a close coupled integral gear motor. In the United States, we define that interface as a C-face, and that defines the bolt circles and the diameter of the register that's machined to locate the motor properly to the gearbox. In the European or metric theater, it's called a DIN flange. Two different standards. They are not interchangeable. And this is a battle between short-term and long-term costs of ownership. The OEMs all use Euro-style gear motors that often have a special motor where the motor, the pinion, the first gear on the gearbox, is actually mounted on the motor shaft. It makes a very compact package. The problem with that is it's a special motor, it's a special gearbox. Gearbox and motor life are not the same. You're going to be replacing your motor more times than your gearbox. especially in continuous duty conveying applications. And therefore, you're locked into a special motor and a special gearbox. You got to go back to the original manufacturer if you use the Euro style. And the Euro style is Nord, Eurodrive, Sumitomo. Sumitomo's not Euro, but it's same style. And as such, and then Lenza, and there's a whole bunch of other guys that are doing it too. The Italians have some brands. That's great at the OEM level, but it sucks for the end user. And I have not been in a maintenance facility at a large end user where outside the maintenance shop, there's not a pallet with a whole bunch of gear motors stacked on the pallet, waiting for replacement from the OEM. The American way of doing things, I think, is a little bit better. And we use a C-face, therefore, C-face motors are stocked everywhere. And instead of a special motor, you use a standard motor. Use a standard C-face input to the gearbox, and Cone added something to that. One of the problems of a metal shaft inserting into a metal hollow quill is that, especially in reversing applications, but over time, those two shafts are going to fret and essentially weld together to the point where you're not going to be able to get them off unless you get a torch on them. And you can't get a torch on them because there's a bell housing around the motor gear interface. It just isn't going to happen. Cone developed the blue bushing technology and patented it. It's basically a shaft condom. Sorry for the abruptness and vulgarity of that, but it helps to remember. The blue bushing prevents metal-to-metal contact. It's a high-density polymer. It transmits torque very well. It's contained between the solid shaft of the motor and the hollow bore of the gearbox quill. It's not going anywhere. It does not decrease the life of the gearbox. People say, why, you're putting plastic in a drivetrain? It doesn't sound very good. Well, we've got a zillion of them out there and millions of hours of operation. And if you want the data for the doubting Thomas, I will get it for you. This is not a problem. This is a benefit. Without fretting of shafts, you take those 4 bolts off, the motor comes apart. Now you can easily change out the motor. The motor is typically going to fail 3 times versus the gearbox. So why would you want to throw the whole gearbox motor away, let alone be sourced to a specific OEM and have to wait to get what you need unless you have it in stock? You can just go out in the motor shop, get a C-face motor. In addition, there's no electrical contact between the motor shaft and bearings and the gear shaft and bearings. And those of you know anything about VFDs know that we induce voltages onto the motor shaft, which tend to find ground through the bearings and cause a problem of pitting in the bearings. This doesn't transfer to the gearbox if you use the blue bushing. Okay. By the way, in this, if you want to learn about epicycloidal and harmonic gearing, there's a couple of video links here, which are really cool, and you can watch them. All right. I have gone beyond my time, and I thank you for letting me do that. We actually haven't really covered everything, but I want to go back to slide 38, where we started, and this is the minimum that you need. What we didn't cover is after slide 38 and slide 39, assuming you can get me the data on slide 39, from slide 40 to 61 is all the work that the applications engineering side does. And I may, with time, talk about that, but this is the presentation associated with that. If you go through this presentation, this is the detail work of getting you a quoted gear motor. And I'm more than glad to go over this with you, answer any questions. It's in the presentation that you've received. So with no further ado, it's 8:15. I've kept you 15 minutes longer. Thank you for staying with me. It's time to go to work, and we'll see you next week.
Thanks, Pierce.
My pleasure.
Pierce. Thank you, Pierce.